This video is going to take you through the second half of chapter 1, which is section 4, 5, and 6. Section 4 is the perimeter and area in a coordinate plane and classifying your polygons. So we start with what is a polygon. The definition of poly means many, and so a polygon is many angles. It is a closed plane figure formed by coplanar segments. Segments here is important because the sides have to be straight lines or segments, obviously, that have endpoints. And it's closed, which means there can be no open gaps. Each side must intersect exactly two sides, so no more, no less, and one at each endpoint. So each side, if this is a side, has to connect to two more, one at each endpoint. No two sides with a common endpoint can be collinear. So you can't have two that extend next to each other. And each endpoint of a side is called a vertex of the polygon. So everywhere those two sides or two segments meet would be a vertex. This first question is just going to ask you to identify the figures that are not polygons. So you're looking for curved edges, open sides, or segments that intersect more than two sides or not at the end point. So if you're looking at A is a polygon. All the sides are segments. There's no open gaps. There's no curved edges or anything like that. B is not a polygon, and it is because of this gap right here. That is not closed in, so it's not a closed figure. C is also not a polygon because these segments, so just this segment alone, intersects more than one segment at its endpoint. D is a polygon, and E is not a polygon because it is not a closed figure and each segment does not intersect two at the endpoints. So you've got this segment intersecting both this segment and this segment, but not one at each endpoint. So the three that are not polygons are B, C, and E. In a convex polygon, no line that contains a side of the polygon contains a point in the interior of the polygon. So none of the sides would extend into the interior of the polygon. If you look at the one in the middle, anything that's inside is called the interior. So if I were to extend each side in both directions, none of those extensions end up crossing into the interior of the polygon. If I do that with the polygon on the left here, neither of those sides would extend in, neither of these sides, neither of these sides, neither of these sides, or here. So this would also be a convex polygon. Same with the one on the right. Opposite of that is called a concave polygon. And a concave polygon has a line that contains a side of the polygon that contains a point in the interior. If I extend a side of the polygon and that extension crosses into the interior of the polygon, it is concave. So if you look at the one on the right first, this segment itself, as you extend it, it goes into the interior. Same thing would happen with that segment. So if it happens with any of the segments, it's concave. If you look at the one on the left, this would be fine, this would be fine, this would be fine, this would be fine. But this segment, as it's extended, would go into the interior, and so would this segment. So this is a concave. Next up is classifying polygons by the number of sides. Hopefully most of these sound familiar. 3 sides would be a triangle, 4 quadrilateral, 5 pentagon, 6 hexagon, 7 heptagon, 8 octagon, 9 nonagon, 10 decagon. There is no special name for 11. It would be an 11gon. 12 is dodecagon, and then anything else is just the number of the sides / GON. All right, this example just says, tell whether the figure is a polygon and whether it is convex or concave. So if you look at A, this is a closed figure, but this segment here in the middle meets more than one at each endpoint. So this is not a polygon. B is a polygon. and it would not have any point cross into the middle if I extend it. So this is convex. C, and specifically 1, 2, 3, 4, 5 sides. 6 stuff. 1, 2, 3, 4, 5, 6 sides. This would be a hexagon. C has this curved edge, which means it's not a polygon. And D is a polygon. This time it's concave because this would cross into it. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. So this would be a dodecagon. Same set of instructions here. It says, well, except that it's asking you to classify the polygon by the number of sides, and then tell whether it's concave or convex. So it's already is a polygon. If you look at A, if I extend it in any direction, it's not going to cross into the interior. So this is convex. And 1, 2, 3, 4, 5, 6 sides, hexagon. B, same thing, extend in all directions, and it wouldn't cross into the interior. So this is convex. And 1, 2, 3, 4 means it's a quadrilateral. And last up, C, this time it is concave. If I were to extend any of these, they're going to cross into the middle. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. So dodecagon. Next up is finding perimeter and area in a coordinate plane. So you can use the formulas given below and the distance formula to find the perimeters and areas of polygons in the coordinate plane. We know perimeter we would find by adding up all the sides. So in a triangle, we would add up all those sides. In a square, you could add up all the sides, or because they're the same, multiply the side length by 4. In a rectangle, you could also add up all the sides, or twice the length plus twice the width. For area on a triangle, it's 1/2 base times height. So if I know the base and I know the height, I can find the area. The square is side squared, so I'd need to know a side length, and then I just square it, and I'd get the area. And the rectangle, length times width. So I'd need to know that length and the width in order to find the area. And those examples will look like this. Find the perimeter of triangle ABC with vertices A, -2, 3, B, 3, -3, and C, -2, -3. And then you're given the coordinate plane. So I'm going to plot first A, -2, 3, which means move left 2 and then up 3. That would be A. B is 3, -3, so I'm going to go to the right 3 and down 3, and that's B. And then C is -2, -3, so back 2, down 3, and that's C. And that gives me my triangle. So in order to find the perimeter, I need to know all 3 side lengths. For the vertical and horizontal sides, I could just count them. So if I wanted to count the length of C to A, it's 1, 2, 3, 4, 5, 6. And C to B, 1, 2, 3, 4, 5. Now to find the third side, which is AB, I'm going to use the distance formula. Distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And it doesn't matter which ones I make, the 1s or the 2s, as long as I'm consistent. So if A is x1, then B would be x2, y2. I'd get the square root of 3 minus a -2 squared plus -3 minus 3 squared. Minus a negative becomes positive, so this becomes the square root of 5 squared plus -6 squared, 25 plus 36. Which is the square root of 61. So 61 underneath the square root would go there. Now, if it gave me instructions that said keep your answers exact, then I would just simply add 5 plus 6 plus square root 61, and I can combine these two, so it'd be 11 plus square root 61. If I had a calculator to approximate the square root of 61, I would just simply type 61 in and then square root it, and I'd get 7.8. If I didn't have either of those things and it wanted you to find the approximation of square root 61, I would know square root 61 is in between square root 49 and square root 64, which means it's between 7 and 8. It's only 3 away from 8, so it's a little bit closer to 8 than it is to 7. So we could have rounded this or approximated it to be a 7.7 or a 7.8, which now we know is the right answer. Then when we add, we'd get 5 plus 6 plus 7.8, or 11 plus 7.8, which is 18.8. And that's the approximation of my perimeter. Here is my exact perimeter. Example 4 says, find the area of triangle DEF with vertices D, 1, 3, E, 4, negative 3, and F, negative 4, negative 3. So this time we only have one horizontal or vertical side. 1, 2, 3, 4, 5, 6, 7, 8 is the length of the base, but I need area. So this is 1/2 base times height. I already have the base, but I need the height. I need it to be a perpendicular segment, so I needed it go from D straight down, making a right angle with that bottom side. And now I can count that distance. 1, 2, 3, 4, 5, 6. So the height is 6. And I'd get 1/2 the base, which is 8, the height, which is 6. I can either do 48 and then take a half of it, which would be 24. Or I can do half of 8, which is 4 times 6, which is also 24. So there's a couple of different ways to do that. I could have done half of 6 and then done that times 8. As long as you only cut one of those numbers in half, or you multiply them together first and then cut them in half. All right, that wraps up 1-4. Now we're going to move into 1-5, which is angles. Hopefully a lot of this is review. We start with what is an angle. So an angle is formed by two rays that have the same endpoint. The rays are called the sides of the angle. So in this diagram, this is a ray and this is a ray. They share the endpoint. And that common endpoint is the vertex of the angle. There are 3 ways to name an angle by its vertex, using 3 points, or if the angle is labeled with a number. So if you're looking at what's here, this could be called angle MNO, angle ONM, or simply angle N. The sides are rays, so they'd be given names in ray form, like ray NM and ray NO. And the vertex is a point. This would be a vertex of N. When you name an angle with a shared vertex, you cannot use just one letter. If I called this angle B, you would not know if I was talking about the top angle or the bottom angle or the big angle even. So when you name a angle that has a shared vertex, you have to use the 3 points. So this top angle would be called angle ABD or angle DBA. Those are the same angle. The bottom angle would be called angle DBC or angle CBD. And the big angle would be called angle ABC or angle CBA. Interior versus exterior parts of the angle. The region that contains all the points between the sides is the interior of the angle, and the region that contains the points outside is the exterior. So the obvious part of this is if you look at a diagram like the one that's here, all of this is the interior, all of this is the exterior. But what about over here? That you would have to picture what would happen if you extended your sides. As you extend it, then you would see that all in here would still be interior and all out here would be your exterior. So just because it's not currently in between them doesn't mean it wouldn't be interior. You'd have to think about extending those sides out. The protractor postulate is a lot like the ruler postulate. On the ruler postulate, we said every coordinate could be given a value and a name. And the protractor postulate says for any ray on the, for any angle, if I line up the bottom side or one of the sides of the angle, the ray of the angle here, then wherever the other side passes through on the protractor would be the value of that angle. Now there's two numbers when it passes through. One is always acute and one is obtuse, except for 90-90, that would be the same. So you have to think about the fact that this is going to be bigger than 90, so that one we would grab the 140. If the angle was on this side, then it's less than 90, I would know that's 40 degrees. So just some symbols here. The measure of angle AOB would be written with the little m in front of it. So the measure of angle AOB is referring to the value of the degrees of that angle. All right, when you're measuring the angles, the protractor is the tool that you'll use, which was the picture we just saw. We measure angles in degrees, and when we classify an angle, there's 4 ways. If it's in between 0 and 90, it would be acute. If it equals 90, it's right. If it's in between 90 and 180, it's obtuse. And if it is straight, then it equals 180, so it would form that line. Example 1 says, find the measure of each angle, then classify the angle. So GHK, it goes in that order, GHK would be that full angle there. So I'm going from 0 all the way up to here. And we know this is obtuse because it's bigger than 90, so it's in between 120 and 130. We're going to say that's 125 degrees, and that would be obtuse. Then you've got JHL, and that one equals 90, and that would be right. Then you've got LHK, which no longer lines up on the horizontal line, so you're going to have to find the distance between these two. So the distance from this is 55 to 90 would be 35 degrees, and 35 degrees would be acute. Congruent angles, like congruent segments, have the same shape and size. So congruent angles are angles with equal measure. You can either write them as the measure of angle A equals the measure of angle B, or, angle D, or angle A is congruent to angle D. So those two are interchangeable based on the definition of congruence. Postulate 4 is called the angle addition postulate, and just like segment addition postulate was important, so is angle addition postulate. And it basically says the same thing. If I take an angle, break it down into its 2 parts, and add them back together, I get the whole thing. Now, what's important here is that point B has to be in the interior of the angle. And then I can say AOB plus BOC equals AOC. If B was not in the interior, let's say it's over here, now that changes all of that. AOB could be here, and BOC could be here. Those would be overlapping. So what's important is that it starts with if it's in the interior of the angle. The second part of this says if angle JKL is a straight angle and point M is any point not on JK, Then if I add those two angles up, JKM and MKL, they would add up to 180 because they form that straight angle. All right, an angle bisector is an angle, or the bisector of an angle is a ray. Has to be a ray, not a, like the segment bisector, you different options. This is a ray that divides the angle into two congruent adjacent angles. So you'll see it written in a couple ways. One, it will literally give you the measurement where they would be the same. Two, you'll have congruency marks. Three, it will say blatantly it is the angle bisector, or it bisects the angle, or it gives you that the two angles are equal to each other or congruent. All right, so now we've talked about the congruency marks before, but this is what they look like. On a segment, there's a single tick mark that would match the other one, saying that those two segments are congruent. In an angle, they have the little red arc usually, and that little red arc means those two have the same measure. And not a congruency mark, but something that we use to show measurement on lines is that little right angle mark, and it is usually red. And it means that it's a right angle or 90 degrees. All right, this example is going to put a lot of that stuff together. It says give another name for each angle. So angle DEB is this angle here. We can also call it angle 4. We can also reverse the order of the letters, BED. We can also use C with it because that would just extend to be the same, CEB or BEC. The next one says angle CBE. Angle CBE, if given a number, would be angle 8. You could also call it EBC by reversing the letters. BEA is next, and BEA would be angle 3. It could also be AEB. DAB would be angle 1. It could also be DAC. Angle 7 is this angle here. Because it only has one angle sharing that vertex, you could actually just call it angle C. You could also call it angle ECA or angle ECB or angle ACE or angle BCE. Any of those would work. Next up is angle 9. Angle 9 could also be angle ABE or EBA. The measure of angle 1 plus the measure of angle 2. So 1 plus 2 would give you this whole angle here, which would be the measure of angle EAB or EAC. Angle 3 plus angle 4 would give you the measure of angle AEC. And the measure of angle 5 and 6 would actually be this full straight angle, angle EDC, or it could have been 180 degrees. Example 3 says, given that the measure of LKN LKN is this big angle here, is 145 degrees. Find the measure of LKM, which is the smaller angle here, and MKN, which is here. So this is where the angle addition postulate comes into play, because that full angle, the 145, is broken down into its two parts. I can add those two expressions together and set it equal to 145. So 2x plus 4x would be 6x. 10 minus 3 would be positive 7 equals 145. I would subtract the 7. 6x would equal 138. Divide both sides by 6. X would equal 138 divided by 6. It's twice and 3 times. So x equals 23. Now what it's asking for is LKM. So I'm going to take my x and plug it into LKM, which would be 2 times x plus 10. I'd get 46 plus 10, which is 56. And then I would do the same thing with 4x minus 3. 4 times 23 minus 3. 92 minus 3, which is 89. Once I found the 56, I also could have just subtracted that from the 45. And I would have gotten the same answer. All right, we're going to move into the last section in this video and in the chapter, which is describing angle pair relationships, chapter 1, section 6. So hopefully we've seen these words before, but these three angle relationships are the foundations of the angles. Complementary are two angles whose measure have the sum of 90 degrees. Supplementary are two angles whose measures have the sum of 180 degrees. And adjacent is two angles that share a common vertex and side but have no common interior points. So adjacent would be, for example, angle 1 and angle 2. These are next to each other. They share a side, but they do not overlap in any way. Non-adjacent would be like 3 and 4 because they are not next to each other. They don't share a side. Adjacent, again, could be like 5 and 6. And non-adjacent like 7 and 8. These are complementary, meaning they add up to 90 degrees. If I were to add the 3 and the 4, they look like they add up to 90 degrees. And these are supplementary, which means they would form that 180 degree line, or if I added them together, I'd get 180 degrees. Example 1 says use the figure to name a pair of complementary angles. So complementary add up to 90 degrees. These are too big. If I do 32 with 58, that's where my 90 come into play. So this would be angle BAC and angle RST. Next up, it wants supplementary angles. So I want two angles that add up to 180. These don't add up to 180, but 122 plus 58 does give me 180. So now I'm doing angle DAC and angle RST. And lastly, it says two adjacent angles. So I want two angles that are next to each other, sharing a common side and vertex. And that would be angle DAC and angle CAB or BAC. Example 2 says, when viewed from the side, the frame of a ball return net forms a pair of supplementary angles with the ground. Find the measure of angle BEC and ECD. So these two form a line with the ground or form a straight angle, which is supplementary, which means 180 degrees. So 4x plus 8 plus x plus 2 would equal 180. 5x plus 10 would equal 180. 5x would equal 170, and x would equal 170 divided by 5, which is 34. Now it's asking for the actual measure of these angles, so I'm going to plug them in. 4 times 34 plus 8. 34 times 4. 136 plus 8, or 144. And x plus 2, which is 34 plus 2. 36. And these two should add up to 180, which they do. Next up on angle pair relationships are linear and vertical angles. A linear pair is defined as two adjacent angles when non-common sides are opposite rays, and they are supplementary. So any two angles whose non-common, which means the sides they don't share, are opposite rays, then they form a line. These are called a linear pair, and linear pair are always supplementary, which means they'd always add up to 180 degrees. Vertical angles, and these are probably the two most important pairings of angles in geometry. The vertical angles are two angles whose sides form two pairs of opposite rays. So if I were to look at angle 3 and I were to extend the angles or the sides of angle 3, they would form angle 6. So angle 3 and 6 are called vertical angles. If I'm looking at 4, the sides of 4, if I extended them in the other direction, would form angle 5. 4 and 5 are vertical angles. Example 3 says two angles form a linear pair. The measure of one angle is 5 times the measure of the other. Find the measure of each angle. So the fact that they're a linear pair means that they're supplementary, which means they'd add up to 180. The measure of one angle is 5 times the measure of the other. So the other angle we know nothing about. We're going to make that x. And the measure of the other is 5 times that, so 5x. If these two together form a linear pair, then x plus 5x would equal 180. 6x would equal 180. And x is 30 degrees. So the smaller measure is 30 degrees. And then 5 times that would be 150 degrees. Double check by adding them together to make sure they give you the 180, and they do. Example 4 says the measure of an angle is twice the measure of its complement. Find the measure of each angle. So a complement means it's 90 degrees. So the measure of an angle is twice the measure of its complement. So if I know nothing about the initial measure, then its complement would be twice that, then twice that would be 2x. And if it's its complement, then it would add. So x plus 2x would equal 90. 3x would equal 90, and x would equal 30. And check by saying if I have an angle that's 30 degrees, its complement is 60 degrees, and that is twice its angle. So 30 and 60 would be the two angles. All right, this one is just more about the visuals. So on the top, it says, here are some things that you can conclude from the diagram at the right. The points are coplanar. A, B, and C are collinear because they lie on that line. Line A, C, B, ray BD, and ray BE all intersect at point B. And angle DBC and EBC are adjacent angles. Angle ABC is a straight angle, and point E lies in the interior of angle BCD. There's no other marking on here to show that anything is congruent, even though they might appear to be. There's no other marking on here to show that anything is a right angle, even though it might appear to be. The only thing you know for sure is that this is a straight angle, and that measurement, that 180, is the only thing you know for sure. What you can't conclude is all the stuff that's here. It looks like this is a right angle, but it's not marked, so you can't conclude it. It looks like these two segments might be congruent, but they're not marked, so you can't conclude it. It looks like these two angles might be congruent, but they're not marked, so you can't determine that. So you can't determine anything by saying it looks like it is. It has to be marked in order for you to know that. All right, last example of the video and the section. Use each diagram to solve for the indicated angle measurements. So in A, you've got two angles that form a straight angle, which means they add up to 180. 3x minus 6 plus 2x plus 16 equals 180. 5x plus 10 equals 180. Subtract the 10. 5x equals 170. Divide by 5. And x would equal 170 divided by 5. 34. Now it wants EFH. EFH is my 3x minus 6. So I'm going to do 3 times 34 minus 6, which is 102 minus 6, 96. The next one says, find the measure of angle ABC. This time you've got a little right angle marked here, which tells us that x plus 9 plus 2x equals 90 degrees. 3x plus 9 would equal 90 degrees. Subtract the 9. 3x equals 81. Divide by 3. And x equals 27. Again, it doesn't want just the x. It wants ABC. ABC is the x plus 9. So 27 plus 9 would be 36 degrees. All right, that wraps up the chapter 1, part 1 and part 2 videos. So make sure you work on the packet, and we will spend time to review together before you take your chapter 1 test.